Welcome back, students. In this video, we're going to look at assigning the designation of R and S to chiral compounds and their chirality centers. First, let's look at two compounds. These two compounds are enantiomers of one another. They have the same connectivity, they have the same chemical formula, but when you put them on top of one another, they're not the same compound. The first one has a chlorine that's coming out of the plane of the page at you. The second one has a chlorine that's going behind the plane of the page. Because these two compounds are actually different compounds, they need to have a designation to illustrate that they're different compounds. And those designations that we use are called R and S. What I want to do is lead you through the process of assigning R and S kind of stepwise. First, I want to show you the entire picture of what you're going to do to assign R and S, and then go more in depth into the sections that need a little bit more help. The first thing that you want to do when you're assigning R and S is to find the chiral center. And you've already had a video on how to find the chiral center, so you can go back and look at that one if you need some more help. Then we're going to talk about assigning priority to each group that's attached to the chiral center. So we found the chiral center, we put an asterisk next to it, and we need to look at each group that is attached, and we're going to have to draw in any hydrogens if we're looking at something that's in skeletal notation. And we are going to assign a priority to those groups. That idea is called the Kohn-Ingold-Prague system, and we're going to look at that a little bit later in this video. A little bit later in this video, we're going to look at step 2 more thoroughly, where we utilize the Kohn-Ingold and Prelog system in order to assign priority to each of those groups. Then we are going to talk about how to rotate the molecule if we need to, because one of the stipulations is to have the lowest priority group facing away from you. And then we're going to look at how, once we've decided priority, and I'm actually just going to show you really quick what the priority is. So it's 1, 2, 3, and 4. Once that fourth group is pointing away from you, what you do is you travel from priority 1 to 2 and then back to 1, where you kind of imagine like 4 is in your hand and you're holding on to that. And when you move from priority 1 to 2 to 3, you then assess, which direction am I going? Am I going clockwise or am I going counterclockwise? And once we know which direction we're heading, we can assign R and S. Let's focus first on that directionality aspect before we go into assigning priority. I've already drawn some fake molecules here where, just to simplify things, I am putting in the priority numerically instead of putting in actual compounds. So 4 is already pointing away from you, and that is a stipulation. You have to have priority 4 pointing away from you. The easiest way to see when priority 4 is pointing away from you is to have it be on a dashed bond. Then we go from priority 1 to 2 to 3 and back to 1. If we're moving in a counterclockwise fashion when we go from 1 to 2 to 3, we call that the S designation. If we are going from 1 to 2 to 3 and back to 1, and we're moving the way a clock turns, that's clockwise, and we call that the R designation. You might be wondering where the R and the S come from, and of course they come from Latin, because why not? For me, when I was a student, the easiest way for me to remember counterclockwise versus clockwise was actually really silly, okay? I'm gonna tell you. Imagine when you're doing the clockwise turn, I imagine that I have like my hands right here. So that's one hand. I'm not a good drawer. That's another hand. And I'm imagining this circle as a steering wheel. And if my hands are on the steering wheel, when I turn right to make my car turn right, I'm moving in that clockwise R direction, right? So that's how I used to link clockwise, that movement of this direction, with the letter R in my brain. So if that helps you, great. If you want to go look up the Latin, go for it. Now let's talk about assigning priority, and then we'll put all the pieces together. Priority is based upon atomic number. What we will do is we will find the chiral center. Once you find the chiral center, you find the atoms that are directly attached to the chiral center. Now notice how I said the atoms that are directly attached. So I'm looking at chlorine, I'm looking at hydrogen, I'm looking at bromine, and I'm looking at the carbon of a CH3. Then I consider the periodic table and I look for their atomic number. Remember on the periodic table that if we're looking at something like hydrogen, the atomic number is the numerical value in the upper left or right-hand corner of the periodic table, depending upon what periodic table you're using. Is the number of protons. You're not looking at mass, right? Not mass, atomic number. If we consider these and we look at the periodic table, bromine has the highest atomic number of this set, so that one is going to be priority number 1. And then comes chlorine, then comes carbon, and then comes hydrogen. So that's how you would assign priority for an example like this. Now what I want to do is make it a little bit more difficult and assign priority again. In this case, I have changed this ever so slightly so that instead of a bromine, I now have an ethyl. We're going to do the same thing. We're going to find our chirality center. We're going to pick out the atoms that are directly attached to that chiral center. And then we're going to start assigning atomic priority based upon atomic number. Here there's a carbon, and here there's a carbon, but there's also other stuff attached to that carbon. Let's talk about that in a moment. Let's do the easy stuff first. Chlorine is definitely number 1 because chlorine's atomic number is higher than carbon and also hydrogen. Hydrogen is number 4 because, nothing gets smaller than hydrogen in the case of atomic number. Now we need to look at these two groups. They both start with carbon. And if you can't tell which one takes priority based upon the two atoms that are directly connected, then you look at the other 3 atoms that are connected. And I like to make a list. I almost kind of think of it like playing cards, right? For this first carbon, we have a hydrogen, and a hydrogen attached. For the second carbon, there are 2 hydrogens there, but there's also this carbon that I just circled. So there's a carbon, a hydrogen, and a hydrogen. So if the original atoms that are first connected don't tell you which one takes priority, then you go to the next set of 3 atoms. And if you look at these 3 atoms, there's a difference between the carbon and the hydrogen. Right? They both have 2 hydrogens. So that doesn't make any difference. But one of them's connected to a carbon. So the ethyl group ends up getting priority over the methyl group. Now I want to forewarn you, this usually introduces a misconception where students will start thinking about size or length in order to assign priority. And I'm going to destroy that misconception pretty soon. So it's not about how big the group is. It's about what atoms are connected immediately to the chiral center. And if that doesn't tell you, you go to the next set of atoms. And if that doesn't make a decision, you go to the next set of atoms. And you just keep doing that until there's a difference. So let's just finalize this and say priority 2 and priority 3. Let's look at our last example of priority. In this group, now I changed it even a little bit more. We still have a chiral center. I still used a hydrogen and a chlorine so that we could quickly identify 1 and 4. Now let's look at what's next. If I look at this carbon and I look at this carbon, they're both carbon. That doesn't do you any good. So what you have to do is look at what comes after that. Each carbon is making 4 bonds. So you've already considered that first bond. You've already considered this connection. So what are the 3 atoms that those carbons are connected to? Let's make our list. I'm going to make the list on the right first because that's easier. This carbon right here is connected to a carbon and 2 hydrogens. So a carbon, a hydrogen, and a hydrogen. If I just kind of erase some of this, right, the hydrogen is here, the hydrogen is here, and the carbon that it's connected to is here. For the one on the left, this is tricky when you get to double bonds. When you get to double bonds, the carbon is connected to the hydrogen that's there, and then it's connected twice to the same carbon. And we're going to count that same carbon, we're going to count it 2 times because we're counting what atoms are connected to the one I'm pointing to right here. And yeah, you've got the same carbon connected, but it's connected 2 times. So we're saying it's connected to carbon once, carbon again, and then hydrogen. And if we compare this set to this set, the one with the double bond takes priority because carbon beats hydrogen. So this side will be priority 2, and this side will be priority 3. Notice how the priority 3 was much longer. Doesn't matter. We're not looking at length, we're not looking at size, we're looking at atomic number of the atoms that are directly attached to the chiral center. And if that direct attachment doesn't tell us what to do, we go to the next set of attachments. Now I want you to do an example. I want you to find the chiral center and try to identify the configuration. I'll come back and give you some help in a moment. All right, first thing, I think you're very capable of finding the chiral center. Now, once you've found the chiral center, we need to find priority. We probably need to draw in the hydrogen. And now let's highlight the atoms that are directly attached to the chiral center. We know that out of bromine, hydrogen, and carbon, bromine has the highest atomic number, so it will be 1. Hydrogen has the lowest atomic number, it will be 4. Then we need to go and look at those carbons. The carbon on the left has attachments of carbon, hydrogen, and hydrogen. The carbon on the right is attached to this carbon that I'm putting the green dot on. It's attached there once and twice, and there's also a hydrogen right here. So which side wins? Well, the one with more carbon. So this gets priority 2 and this gets priority 3. I'm going to go ahead and redraw this to not muddy up our work so much. So I'm just going to redraw this down below and say priority 1, priority 2, priority 3, priority 4. And now what I'm going to do is go from priority 1 to 2, 2 to 3, and back to 4. Notice my hydrogen, my lowest priority group, was already pointing away from me, and I'm moving in that clockwise direction, so this is going to be R. Now, if you needed some support before you try the second one, go ahead and pause again. Otherwise, if you're ready to go through the second one, we can go ahead and do that right now. For the second one, we already found the chiral center, and I want to highlight the atoms that are attached to the chiral center. I'm going to have to draw in that hydrogen. Oxygen and hydrogen are very clearly 1 and 4, right, because carbon is your other option. And we need to stop and we need to look at this carbon versus this carbon. So the carbon on the left, it's attached to 3 different carbons. It's attached to this one, and this one. The carbon on the right is attached to the carbon of the double bond, which I'll highlight in blue. It's attached once and twice, and then there's a hydrogen here that it's attached to. The one that gets priority then is the tert-butyl group, so this gets priority 2, and this gets priority 3. There's a lot going on when you're assigning priority, so just have some scratch paper nearby. It's can get pretty messy. So I'm just going to redraw so I don't end up having this get too overwhelmingly messy. I'm going to put in my priorities again. So 1, 4, 2, and 3. And I'm going to go from 1 to 2, 2 to 3, back to 1. And that is going counterclockwise. So that is S. Great work. Let's go to a harder example. In my harder examples, what is going to happen is that your lowest priority group is not going to be automatically pointing away from you. Those last two that you tried, I purposefully put the lowest priority group pointing away from you, because if you don't do that to begin with, there's too much for your brain to consider and it gets overloaded. So let's pretend that we don't have our lowest priority group pointing away from us. What are we going to do? Well, even before we get into that situation, I want to tell you something really quick. I want you to know that if I go back to a very simple drawing like I have here, if I take any two groups in my compound, I find my chiral center, it's right here. If I take any of the two groups on that chiral compound and I switch where they are, I have changed the configuration. So the first one here is going from 1 to 2, 2 to 3, back to 1, that's S. I switched the 2 and the 3, and now I'm going 1 to 2, 2 to 3, back to 1, and this is R. So if I take any two groups, it doesn't matter which ones they are. It doesn't matter if it's the wedge and one of the ones in the plane of the page, or if it's the two in the plane of the page, or the wedge and the dash, and I flip them. I flipped the configuration of the compound. We're going to use this to our advantage. Let's look at this example down here. Right now, I have a simplified example where priority 1 is pointing away from you. You don't want that. You want priority 4 to point away from you. What we're going to do then is we're going to take priority 4, which we want pointing away from us, and the thing that's already pointing away from us, and we're going to flip their locations. So we're going to put priority 4 here, and we're going to put priority 1 here. We're going to keep priority 3 here and 2 here. So we flipped 1 and 4. When we flip any two groups, we change the configuration. So we actually just changed, even though we're trying to rotate a molecule, we changed the configuration from the first drawing to the second drawing. So now, in order for us to rotate the molecule without engaging our brain so much that it hurts, what we'll do is we'll take any two other groups and we'll flip those. So if I take this group, say, and this group, and flip them, then I'm rotated back to my original compound. But the beauty is, now that I've flipped the 3 and the 2, so my 2's up here and my 3's down here, my 4 is now behind the plane of the page. It's pointing away from me, and that's what I needed. Now, a lot of textbooks will say, you know, take your 4th priority group and put it on the dash bond, so flip 2. And then flip the other 2 remaining groups, but in actuality, it doesn't matter what other 2 groups you flip. It would just be dumb to flip the 4th group. Don't do that. You wanted to get the 4th group on the bond that's pointing away from you. And maybe it's just easiest for you to say, I flipped these 2, so I'm going to flip the 2 I didn't flip earlier. But really, it will work with flipping any 2 sets of groups. So how do we take what we've learned and incorporate it into IUPAC nomenclature? And that's what I want to look at. First, let's draw in our lowest priority group, which is that hydrogen. Our chlorine is priority 1, this is priority 2, this is priority 3, this is priority 4. And we can go through and say 1 to 2, 2 to 3, and back to 1. When we do this, then we're saying that this is an R configuration. We already know how to name the rest of the compound. We know that this is 2-chlorobutane. In order to incorporate the R, we just put the R out in front. A lot of times you'll see the R written in parentheses, and there will be a dash between the R and the locant. If there are multiple chirality centers, we change the format of this a little bit. First of all, you might just want to test your skills to see if you can come up with the fact that this one and this one are both R in configuration. Then, once you're capable of doing that, we can learn how to put the whole name together. In this case, I've numbered my different locations 1 and 2. So I would call this 1R, 2R, and that would be in parentheses. And then I would continue my name by saying 1,2 dimethyl cyclohexane. The reason that I have to put in the locant next to my R configurations is because you need to tell the reader where the chiral center is when you have more than one of them. So you have to put in the locant for the chiral center when you have more than one of them. And then this is just what you would expect your regular name to be. You also have to tell the reader where the 2 methyls are, that they're at the first and the second position. Let's wrap up. In this video, we looked at the designation of chirality centers. We talked about how to designate R and S and went through all of the steps, and then we did some practice. We also talked about how to rotate the molecule and how to incorporate the R and S designation into chemical nomenclature. Thanks so much for watching. This is Katoni signing out.